so I want to start by talking more about topological equivalence, which I defined last time. So let me remind you of the definition. So recall that we say X and Y are topologically equivalent, notated like this, if there exist continuous maps between X and Y, which are continuous bijections and inverses of one another. We can write that as G composed with F is the identity on X, and F composed with G is the identity on Y. And in this case, we say F from X to Y is a topological equivalence. And similarly for G. Okay, so let's see an example. So we did some examples. Last time I want to do basically some more examples now. So let's define a space Xn as follows. So it's, so you get it from taking a sheet of paper. Should have done this beforehand. Let me rip this up. So you take a thin strip of paper and then you put some number of twists in it. It's hard to do more than 2 on this. And then you glue the ends up like this. So I'll draw that like this. So we have some number of twists. And then, well, okay, so this is my picture here. So in this region, we have n twists. So, okay, so let's see concretely how this looks for some small values of n. So when n is, so n here can be anything, any integer, at least 0. When n is 0, sorry, let's do this. So x0 with 0 twists, this is just an annulus. So this is what we call the annulus. Topologically, it's S1 cross an interval. Or S1 is the circle. I want to continue on this page. Sorry, let's. This is maybe questionable board work, but let's do it anyway. Okay, so x0 is that. x1, when we have 1 twist, looks like this. This is called the Mobius band. It's like a twisted version of this product, S1 cross I. You can see this, for example, on my webpage, or also if you go to the engineering, in front of the engineering building, they have a large physical copy of it. So x2, well, okay, so as we go on, then, okay, so then you can sort of imagine what x2 looks. We're going to draw x2 and so on. Okay, so we're talking about topological equivalence. So you can ask, which are any of these topologically equivalent? And so I claim that, well, in fact, x0 and x2 are really the same space. So topological equivalence is our way of saying that two objects are really the same, although they might look different in some way. They're really the same topological space. So let me try to convince you of this. So here's a way to draw these spaces. So here's another way to represent it. So we take our strip of paper and then we glue the left edge to the right edge in this way. Let's do this also for the Mobius strip to see how it's different. With the Mobius strip, we glue with a twist. So we glue in this way. You identify them with the twist like this. And then x2, I guess I would draw it this way. Well, we twist twice, and then we glue the ends like this. But notice that, I mean, this shape is the same as this one. I mean, you can imagine well, okay. I mean, I guess I'm just saying that there's a obvious bijection. So let me put it this way. So the proof, there is an obvious bijection. Between these two. Just point to it here. I mean, yeah, maybe let me just leave that to you to think about as an exercise. And it's maybe worth thinking about why there's not an obvious bijection between these two. But of course, the gluing in these two is different. So there's no obvious bijection here. Okay, so this is telling you something about topological equivalence. It's right. It's different than how the space is represented in R3. The definition is just that there is a continuous bijection with a continuous inverse between these two. And in this case, you have that. Let me say a little bit more about these spaces. So similarly, x0 is topologically equivalent to x2k for k, for any k, by the same sort of argument. And x1 is equivalent to x2k plus 1. So any of the odd versions of this space are also topologically equivalent. On the other hand, x0 is not equivalent to x1. And you can see this by comparing the boundary. So, well, okay, so So let me explain this at least intuitively. So here's x0 and x1 again. And let's just look at the boundary. So for x0, the boundary is 2 circles. So boundary of x0 is S1 disjoint union S1. And the boundary of x1, well, so we go around like this, and we come down, and then back up, and come around. So the boundary here is 1 circle. And these two are not topologically equivalent. Oh, so this was supposed to be a not there. These are not topologically equivalent, and the reason is their boundaries are not topologically equivalent. So the statement is if x0 were equivalent to x1, then the boundaries would have to be topologically equivalent. So this requires proof. And we don't quite have the tools to do it now, but this is at least the idea for why these are actually different spaces. You just look at the boundaries. As a further illustration of this idea, x0 and x1, or x0 and x2, well, these cannot be deformed one to the other in R3. And, well, some terminology, we say they're not isotopic if you can't deform one to the other in ambient space. And the way to see this, again, is by looking at the boundaries. So for the annulus, again, well, okay, for the annulus, we see we have, well, let me draw the other one. That's the interesting one. So for this x2, let's look at its boundary. And the key is to keep track of how it sits inside of R3. So we know that the boundary is going to be 2 circles because it's topologically equivalent to x1 or x0. But the way those circles sit inside of R3 is interesting. So here, here the boundary is an unlinked circles. And here we have linked circles. So the picture is like this. This is a non-trivial link. And so the fact is that if you can deform x0 to x2 in R3, then it would have to be the case that you can deform the trivial link to this non-trivial link. And, well, if you just had a physical link, you would probably be quite convinced that you can't deform this one to the other. Of course, mathematically, this requires some proof, which eventually we'll be able to give. But okay, right now we're working a little bit on intuition. Okay, so I want to give a couple more examples. illustrating this concept of topological equivalence. So let's take T to be the torus, which is S1 cross S1. So previously I've just drawn the torus like this. You can think about it as the product of S1 with itself, because you have you have these two circles, and I guess one way to say it is for each point on the blue circle, there's a circle like this. So you have a circle's worth of circles, which is this product space. So actually, I want to think about this space a little bit differently. So we could think about it as the product. Often in topology, it's useful to have a bunch of different descriptions for the same space. That's useful for manipulating spaces and making arguments. So another way we can think about this is you take an annulus and you identify the two boundary components in this fashion. So let me draw one more picture. So here's that annulus. I'm just drawing it slightly differently. And you're supposed to imagine that you take those two circles and then you join them together, and then you get the torus. But here's an interesting twist. There's a different way to start with the annulus and to glue the two circles. So alternatively, we could consider let's draw it this way. The annulus where now I glue in this way. So the picture is sort of like I take these and instead of, well, okay, and the gluing now is matching them like this. So I just identify these two circles sort of by just a translation as it is in this picture. Whereas this gluing is kind of like, well, you might say it's a reflection. But this terminology is potentially confusing. And if we do this, we get a different space. So this gives a different space. Which I'll call K, which is called the Klein bottle. So it's a little bit hard to draw a picture analogous to this picture because the Klein bottle, it doesn't, you can't embed it in R3, but the closest thing to a picture you might draw is something like this. So here it's crossing itself, but well, okay, so this is meant to be a schematic picture. Okay, if all of these pictures you're not happy with these pictures, let me draw yet another one. Well, the more pictures you have, the better, at least in my opinion. So here's another picture of the torus, and then I'll draw an analogous one for the Klein bottle to compare. So I'm cutting the annulus along this edge. So that is now becoming this edge, and I get a disk with some side identification. So the edges, or labeling the edges in this way, is just meant to tell you how to glue. So you take the red edges are the same and the blue edges are the same. If you can tell that that's blue. And so, okay, so you first glue the red edges to get an annulus, and then you glue the blue edges to get the torus. Okay, so these are all the same pictures of the same space. And the version for the Klein bottle is like this. So, okay, you have the top edges glued as before, but now, right, so if we cut this apart, then what we find is that the orientation here is different. So this is similar to like in the Mobius band. Mobius band versus the annulus. So these differ by a different choice of gluing. Okay. So, okay. Right. So maybe I'll state it as a theorem that the torus is not topologically equivalent to the Klein bottle. So doing this gluing in a different way actually gives you a new, different space. Okay, we'll prove this later, eventually, once we know about fundamental groups. Okay. One more example. Which is an example I like quite a bit. So these are linked rods. Okay, so consider the following linkage. So here's the picture. I have two rods. They're connected end to end. One is blue and one is red. They both have length 1. And I'm going to keep this endpoint fixed. So this is fixed. And then I let the rods move. The rods can swing, rotate around. This rod rotates around this circle, and then, this rod can swing around the circle around this point here. So this is the linkage, and so I want to consider the configuration space. So let me call it X. And the configuration space just tracks all of the different possible positions for the linkage. So this endpoint here is fixed. Let's say it's fixed at the origin. So we're working in R2. And we have the position of this one point, this one endpoint of the first of the blue rod, and then there's this endpoint of the red rod, Z2. And I just want to know all the possible positions of Z1 and Z2. So the configuration space, it's all the possible positions of the linkage, but I can write that a little more precisely as its possibilities for Z1 and Z2. And we could write an equation for what is required. So here's Z1 and Z2 are in R2. And, well, we can describe explicitly what has, these points, what these points are. So first of all, Z1 has to be distance 1, that's the length of these rods, from the origin. And the distance between Z2 and Z1 is exactly 1. So, okay, so for any such pair like this, there's a position of the linkage. And every position of the linkage gives you a pair. Okay, so this is the configuration space. Okay, let me give you another linkage. So, okay, I mean, these spaces are very interesting. They're the kind of things that you might consider if you're interested in robots. I mean, you can think about this linkage as, these are like arms of a robot, and you want to know what are all the possible positions of those arms. Here's another linkage that you'll think a little bit more about in homework. So this one has 4 rods. Let me draw it this way. And the endpoints are going to be fixed. Now both endpoints are fixed here. But then these points are allowed to move around. So this is fixed, fixed, and these move. So we have now Z1, Z2, Z3. And similarly, you could write an equation for its configuration space. So it's possible positions of Z1, Z2, Z3. I wrote Z3 twice. And now, you could write equations. So Z1 is distance 1 from this point. Maybe this is the origin. Z1 and Z2 are distance 1 apart. Z2 and Z3 are distance 1 apart, etc. So a cool fact is, well, you can think about what is the dimension of these configuration spaces. So let's let Y be the configuration space for this linkage. Okay, so related to topological equivalence, you could ask, well, are these topologically equivalent spaces? So we have these 2 spaces. This is a general question you can ask. You're given 2 spaces, are they topologically equivalent or not? So one thing that suggests that they could be topologically equivalent is to just think about what their dimensions are. So dimension count. Well, for X, so you have 2 variables. Each of these Z1 and Z2 cannot, at the beginning of the day, Z1 and Z2 are just in R2. So that's 4 degrees of freedom. But then you have 2 equations. So by a dimension count, X is 2-dimensional. And, well, let's think about Y. So the equation for Y is, well, the equations that define Y, maybe I'll call this point here P. You have, well, Z1 has to be distance 1 from the origin. Z2 minus Z1, that distance is 1. Z3 minus Z2, that distance is 1. And then P minus Z3, that distance is 1. So there's 4 equations. So here you have the parameters. There's Z1, Z2, Z3, each are in R2. So that's 6 degrees of freedom. But then you have these 4 equations. And so that cuts it down by 4. And so Y is also 2-dimensional. Okay, so potentially they are topologically equivalent. And you'll think about this a little bit more on the next homework assignment. Okay, so the point of all of this, I just want to introduce you to some interesting topological spaces. And the basic question, whenever you have a topological space, you can ask if they're topologically equivalent. So let me just remark on that. So this is a basic problem in topology, and this is one of the type of problems that we'll think about a lot in this course, is to determine, so let me say, given X and Y spaces, determine if X is topologically equivalent to Y. Right. So let me tell you about one more. So let me tell you, one more example. I'll state it as a theorem. If P and Q are polyhedra, then if P is topologically equivalent to Q, then the Euler number of P is equal to the Euler number of Q. Remember, this is vertices minus edges plus faces. So let's see. Well, the reason I'm telling you about this theorem is because it gives you a tool to test whether 2 spaces are topologically equivalent or not. So as a consequence, if you have 2 polyhedra and they have different Euler characteristic, Euler number, then they're not topologically equivalent. So for example, the cube has Euler characteristic 2, and whereas the torus polyhedron has Euler characteristic, sorry, I didn't mean to write chi 2. Let's say chi is equal to 2. To torus polyhedron, we computed chi is equal to 0. And so these are not topologically equivalent. And while the cube is topologically equivalent to S2, we discussed this sort of thing last time, I believe. And the torus is topologically equivalent to, well, the torus. And so this is an argument. This theorem gives you a way to show that the torus and the sphere are not topologically equivalent. Right. So I wanted to remark that we proved a special case of this theorem. maybe I'll just, yeah, 1 second. Okay. So I think my face is going to be covering some of this text, but I guess you have the slides to look at anyway. So, right, so remark, well, we proved a special case. So if P and Q satisfy the assumptions of Euler's theorem, so right, they're connected and any loop separates P and Q into two pieces. So then, well, last time we gave an argument showing that P and Q are both topologically equivalent to S2. And so in that case, we have the setup of this theorem. We have two polyhedra and P is topologically equivalent to Q. And so the theorem predicts that P and Q have the same Euler characteristic. So let me say it this way. So the theorem predicts chi of P is chi of Q. And indeed, by Euler's theorem, chi of P is 2, and same for chi of Q. Okay, so this theorem generalizes Euler's theorem. Yes, I just want to say that this theorem is a quite important theorem, and it dates back to Euler, I believe, and it's one of the theorems at the birth of topology. So this is one of the first, results that lets you distinguish topological spaces. Okay, we'll discuss this more later. So I want to now switch gears and talk about something a little bit different. Okay, so topological spaces. So I haven't given you a definition of what a space is at this point. We've seen lots of examples, but we want a general definition which is going to apply to a broader class than just the examples we've seen already. So here's what we want. A general definition of space, of a space, that includes all the previous examples previous and future examples, so and more. And roughly, a space is a set with some extra structure, which we'll see what that extra structure is in a second, so that it makes sense. Sorry, I'm getting sloppy. Makes sense to talk about continuous functions. So we saw when we discussed topological equivalence, it relies on a notion of continuous function between the two spaces. And so we'll need our definition to, we want our definition to, whatever our definition of topological space is, we had better have a notion of continuous functions between two spaces. Okay, so I want to lead up to the definition of a topological space. But before we get there, let me remind you the definition of continuity from analysis, I guess. So recall a function from Rn to Rm is continuous if for each x in Rn and epsilon greater than 0, there exists some delta so that, okay, so I'm going to write the condition like this and then explain the notation. The delta ball around x maps into the epsilon ball around f of x. So here, b delta of x, these are the points, let's say y in Rn, so that x minus y is less than delta. And so the picture is we have x in the domain and f of x in the codomain. We're given x and we're given some epsilon, which gives some ball of radius epsilon around f of x. And so here's the radius epsilon. And continuity means, given this input, we can find sufficiently small ball around x, radius delta, b delta x, so that under f, this ball maps into this ball. So whatever it looks like, it maps into the ball here. Okay. Right, so there's an equivalent definition of continuity, which is phrased in terms of open sets. So let me tell you what that says. So we say a subset of Rn, or let me put M, Rm is open if for any u, for any y and u, there exists some, let's say epsilon greater than 0, so that the ball of radius epsilon around y, let me use r, I think it'll be a little less confusing. If there exists r greater than 0, so that the ball of radius r around y is contained in U. So for example, open subsets of R, of the real numbers, these are unions of open intervals. So something like this. This is an open set. And on the other hand, closed intervals are not open, as the terminology suggests. Although you have to be a little careful because, well, okay. So if instead we took a closed interval, so we include the endpoints, then this set is no longer open because around this green point, every small ball, any radius r, is not going to be contained in this set. Right, so we can restate the definition of continuity. F from Rn to Rm is continuous if F inverse of U is open for every open subset U in Rm. Okay, so the pre-image of an open set is open. So this is the pre-image here. This is X in Rn, so that F of X is in U. All right. Okay, so the key thing that you need, so the upshot of all of this is that the key thing that you need to define continuity is a notion of open sets. You can define continuity once you know what open sets are. Then you can say this sentence: F inverse of U is open for every open subset. So a topological space is going to be a space with a collection of open sets, satisfying some properties. So the basic properties of open sets in Rn motivates the following definition. So a topological space is a set X together with a collection of subsets of X, which are called open sets, so that, well, we want the following properties. So first of all, X and the empty set are open. They're in this collection. Arbitrary unions or I could just say unions of open sets are open. And finite intersections of open sets are open. So open sets in Rn as I defined them on the previous page, satisfy these properties. If you take a union of open sets, you get something open. All of Rn is open, the empty set is open vacuously, and finite intersections of open sets are open. So we define a topological space is a space, it's a set together with a collection of open sets which satisfy exactly these properties. So let me just point out that this is a very abstract definition and it takes some getting used to. But the wonderful thing about this definition is then we can define continuity. So definition, if X and Y are topological spaces, then a function from X to Y is continuous if F inverse, well, let me say it this way, if for each U and Y open, F inverse of U, which is a subset of X, is also open. Okay. I want to finish with just a quick little example of how to think about some of the examples we've seen as topological spaces. So example. So if X is a subspace of, let's just say R3, we can make X into a topological space by defining or by declaring that sets of the form U intersect X are open when U is an open subset of R3. Okay, so exercise, this defines a topology on X, which is to say that this collection of open subsets of X satisfies these properties 1, 2, and 3. So, for example, let me finish just by drawing some pictures of some open subsets. Let's take X to be the cube. Well, an open subset, well, one way to get an open subset is to take an open ball and intersect it with X. And in this way, you can get things that look like, well, you can get, like a little patch here. Or you can get something sort of like this. If you take a little ball centered around a vertex, you get kind of a picture like this. And so on. I mean, an example of an open set, you can get an entire face, the interior of a face. Etc. So, okay, hopefully this gives you some idea. These are also open sets. One more picture example, if we were to take the torus, then, well, again, if you take a small ball and if maybe you pick, let me say it this way. If you pick your favorite point and take a small ball around that, then intersect it with the torus, then we'll get some small little disc like this. And it's important to remember that unions of open sets are open. So if you do that for some sort of region, then you can get open sets that like cover maybe the right half here, and so on. Okay, so this is, yeah, so like I said, getting used to the definition of a topological space will take some time, and we'll spend a little bit of time next time seeing some more examples. All right, let's stop here.